Okay. Set and logics. Okay. Set is a collection of objects, and logic is the study of reasoning. And reasoning consists of verbal reasoning and non-verbal reasoning. And mathematical reasoning is in the part of non-verbal reasoning, which is critical in the study of computer science. In the Star Trek 4, this sentence was said. It says, logic, logic, logic. Logic is the beginning of wisdom. Valeries, not the end. So here, what it means is logic is the beginning of wisdom, but not the end. That's what it was announced. Okay, yeah, you know the definition of set, and you know the notation of the set, and these are the symbols that we're going to use. The n is a set of natural numbers, I is the set of integers, and q is the set of rational numbers, and r is the set of real numbers, and g plus is the set of positive integers, and g minus is the set of negative integers, and g non-negatives is the set of non-negative integers. I can make it a little bigger. Here. So yeah, we will use these notations, and like the author prepared. When you count the number of elements in a set, we use this notation. So if X is a finite set, then the cardinality of X means the number of elements in the set X. This is a notation. So we read it as the cardinality of X, like this. And so in this case, the cardinality of A is 4 because it has 4 elements in it. If we have two sets, the element of two, the set of 2 elements like this, R and G, then this set has 2 elements, so the cardinality of this set is 2 because it contains 2 elements. Okay, here, and also X means X is an element in the set X. Okay. This means, the implies, and these notations are all same. Here, you know the empty set, and this is a notation for the empty set. When 2 sets are equal, then, which means it has the same element. So like this, if this set A has 3 elements, 1, 3, 2, and this set B contains 3 elements, which is 1, 3, and 2. So basically, this 2 set has the same element 1, 2, and 3. So they are same set. They are equivalent. Later, we will learn the multiple sets which distinguish these 2 sets. But now, we only just count the distinct numbered element in a set. Here, these are the I will go just briefly. Subsets, and what next? These are the simple examples, and proper subset. Proper subset. If X is a subset of Y, but X is not same as Y, then we call X is a proper subset of Y. And the power set of X. If we have a finite set of finite elements X, then the set of all subsets of a set X is denoted as P of X that include all subsets of X, including including X itself and empty set also. This P of X is called the power set of X. So for example, if we have a set of 3 elements A, B, C, then power set of A should looks like this, and the number of elements should be 8. Usually, the power set of a set with n element has 2 to the n element, as you know. And now we define union and intersections and differences, as you know. Yeah. And this set for the complement. But for the notation, the set difference x minus y is defined as the set of elements that satisfies x is in x, but x is not in y. We call this set is a difference or a relative complement. So the difference x minus y consists of all elements in x that are not in y. So in this case, the a minus b is we exclude the y, so 1 and 3 is left. But for b minus a, we eliminate 5 from b, so we have only 4 and 6. So as you see, for the difference, the a minus b is not same as b minus a in general. And r minus q means the set of irrational numbers, because we eliminated all rational numbers from the set of real numbers. So only the irrational numbers are left. Okay, and disjoint, yeah, you know the meaning of disjoint. If the intersection is an empty set, we call those two sets are disjoint. And if x and y's are distinct set in S and x, y are disjoint, then the collection of set is pairwise disjoint. Suppose we have a big set S and we have many finite disjoint finite subsets in it, then every pair of two sets are disjoint, then we call this whole set is pairwise disjoint. Okay? If all the subsets is pairwise disjoint. pairwise disjoint. 그러니까 어떤 큰 집합의 부분 집합들이 여러 개 있는데 부분 집합을 2개 골랐을 때 다 디스조인트면 그 2개가 디스조인트하다고 하고, 그 S 안에 있는 모든 부분 집합들이 다 페어와이즈 디스조인트 하면 S의 부분 집합 모두가 그냥 페어와이즈 디스조인트 한다고 얘기를 해요. So pairwise disjoint. That's the concept. Example next. And here, this is an example of these are all. This we have S has a 4 element here, and each set are pairwise. Each pairs are disjoint. So this set S, the collection of sets, are pairwise disjoint. And U, this notation U is used for universal set or universe. It's everything actually. Then given a universal set U and X is a subset of U, then the set U minus X is the complement of X. It's just complement of X here. So U minus X can be written as X bar or X complement like this. Okay. The universal set and subset, then complement of subset is denoted with these notations. And here, G non-negatives are, if the universal set is G, then complement of negative integer, the complement of the set of negative integers can be written in here, written like this. Yes. It's a G non-negatives only. The non-negatives means G negatives complement. Okay, then everything's are non-negative integers. Okay. Anyway, next is Venn diagram. Venn diagram was invented by John Venn, who is a British logician and philosopher. And you know what this means. This is the union of A and B, and this is the A minus B, and this is the intersection of A and B. Okay, with this, this example 1.20 shows you, suppose we have 165 students and 8 are taking calculus, psychology, and computer science, and 33 are taking calculus and computer science, and 20 are taking calculus and psychology like this, and 24 are taking psychology and computer sciences, then something like that. Then we can draw the Venn diagram like this, and we can find this. How many are taking none of the three objects? Then, so first, then what we are looking for is this complement here. So we find the union of these three sets, and then subtract this number from the whole student body. Then we will have 9 here, like this. So the Venn diagrams are used to compute those. And these are the rules for the union and intersections that you have learned before. And these are the notations for union and intersections, for finite and for the infinite sets. And here, partition. I think this may be a first new concept for you, for most of you. Partition. A partition of a set X divides into non-overlapping subject. A collection S of a non-empty subset of X is a partition of a set X if every element in X belongs to exactly one member of S. And what this means can be written in mathematically like this. X is a union of all those sets, but each of SI's are pairwise disjoint. Okay? In this case, if S is a partition is over X, then S is pairwise disjoint. What this means is, suppose you have a pan of pizza, then if you cut it to 8 or 10, then if you make a union of all those 8 or 10 pieces, then you will make whole pan of pizza, but each of those small pieces, small slice of pizzas are all disjoint. So that's it. So when you have a full set, if you can just cut it out without any intersections, then those slices are called as a partition of the whole set. Okay. This is important when you do count. When you want to count everything, then you may have to slice each cases and count on each cases to earn the whole possibilities. Okay? So this is an important concept that you're going to see over and over again. So here, like this, we have you have 8 element set like this. Then these 3, 2, 1, 2, these 4 sets are pairwise disjoint, and if you find the union of these 4, then that forms the whole set X. So this S form a partition of the given set X. And order the pairs in Cartesian product. Cartesian product. X and Y's are sets, and Cartesian products X and Y, X cross Y is the set of all ordered pairs, where X is in X and Y is in Y. This X cross Y is the Cartesian product of X and Y. We read this notation as X cross Y. Okay. So X cross Y is a set of all this ordered pair, X and Y, where X comes from X and little y comes from big Y. And for arbitrary finite set X and Y, the cardinality of this Cartesian product of X and Y is same as the product of cardinality of X times cardinality of Y. This is always true for any arbitrarily finite sets X and Y. Same thing works for n when the cross Cartesian product of this n set. Okay, this this is also a Cartesian product of this n set, and cardinality of this cross product, the Cartesian product of xi's is same as the product of cardinality of each set xi's, like this. Okay. Next, proposition. Okay. Before we start the proposition, since first class hour is up, so we will take a 10 minutes break. Any questions on section 1.1? Okay, then let's take a short break.